I would like to start by thanking Shri and Nikhayam for putting together this session. For my presentation, I'm going to talk about the recent developments that we had in the MAGMA library regarding FP16. And I'll be focusing mostly about mixed precision linear solvers. So what we already released in MAGMA, so we had 2 releases with FP16 developments. So starting MAGMA 2.5.0, this is mostly the work by Azam Haider. This release provides a triple precision solver for solving AX equal B for general matrices, so using LU factorization with partial pivoting. And you can get up to 4 times speed up against doing the full solve in FP64. And this was originally inspired by this paper by Carson and Hayam about using GMRes-based iterative refinement instead of the classical iterative refinement. And the implementation is highlighted in this SC 2018 paper by Azam from UTK. We had the second release, 2.5.2, where we had our first in-house kernel that uses the tensor core on NVIDIA GPUs. This is a batch matrix multiply kernel for fixed sizes. It is faster than BLAS if you are testing on sizes less than 100. And other than that, it is competitive if the sizes are not multiple of 8. This is because I think BLAS uses some vectorized reads and writes, which we do not do yet in our developments. Now for the ongoing stuff that is to be released. So we are looking to provide wider coverage for triple precision solver, basically extending support to complex systems, complex matrices in single complex and double complex precision, as well as a Cholesky-based solver for symmetric positive definite matrices. The main thing that is common across all these developments is that we do not do the full factorization in FP16. So we do mixed precision factorization using mixed precision BLAS, meaning that the factorization will happen in single precision except for the dominating steps, which are the rank K updates. This is where we use the mixed precision BLAS, and this is all thanks to the tensor core units in current NVIDIA GPUs. So the big picture is that we start, this scheme works for both single and double precision. So if your matrix is in double precision, you have an extra step of converting to single precision, and then you do mixed precision factorization using mixed precision BLAS. And this mixed precision BLAS, you have a form of C equals C minus A times B. So A and B are converted to half precision, to FP16, and then shipped to the tensor core kernels that can accumulate in FP32. And this is where all the performance gain comes from. So this is the advantage that we take here by using half precision instead of single precision. And if you have a single precision matrix from the beginning, you don't need to go through this conversion step. So this works for both FP32 and FP64. Now, the second step, which does not have any performance gains, we are trying to recover the solution back to the accuracy of single or double precision. So this is called iterative refinement. We begin by residual, compute the residual, and then solve a correction equation here, and then add the correction vector to the solution until we converge. So classically, we had this done by using direct triangular solves using the low precision factors of A. But now we can use preconditioned GMRes instead of the triangular solve, and this proves to be much more stable than classical iterative refinement if we are using FP16. Now, in order to add support for complex matrices, we need to have half complex computation, and this is something that's not natively supported by the vendor libraries as of today, I think. So if you would like to use the vendor libraries like BLAS LT, or open source packages like Cutlass, you have to go through split complex format. So you have to separate the real and imaginary components of the matrix in order to use these libraries, which can be good if you are close to the peak of the GPU. So this is if you'd like to use the vendor library split complex or planar layout. We still believe that using the standard interleaved layout for half complex will be beneficial, especially if we are doing rank K updates, because these rank updates do not hit the peak performance of the GPU, and these have better arithmetic intensity than doing a full split complex computation. So what we are looking for is a CGEM kernel, so single complex matrix multiply, that is accelerated by FP16. So if we are willing to use cuBLAS, we have to call cuBLAS 4 times in order to do real imaginary and real and so on. And this will have this formula of the arithmetic intensity, so the ratio between flops and bytes. If you do an interleaved kernel, interleaved layout, half complex, we will have double the arithmetic intensity, and so there is room for more performance, even if we are not using the same optimization that cuBLAS is famous for. And these are theoretical bounds, so these are roofline models for rank K updates of size 256 on the left and 512 on the right. You can see that for cuBLAS, no matter how cuBLAS is optimized, we are not hitting the GPU peak here, so it's still kind of memory bound. So if you use cuBLAS, there is no way that you can get through 60 teraflop of performance. If you are using interleave layout, you can go up to actually more than 100 teraflops of performance if you have the same optimizations that cuBLAS does have. If you go for a wider panel, 512, then you can actually hit the GPU peak performance with interleaved half complex, and you can saturate at 100 teraflop if you are using split complex. So the interleaved half complex format is theoretically better, and we will see that with actual results. So what we do, we developed a kernel, so we have a lot of matrix multiply kernel in MAGMA for several reasons. So we extended some of these techniques to support tensor core with FP16. So we build an abstraction layer over these tensor cores to support any blocking sizes in order to perform our usual auto-tuning frameworks. And these are actual results for rank K updates and of two sizes. So on the left, this is MAGMA with interleaved half complex, and this is cuBLAS with split complex, so 70% better if you are using the interleaved format. And again, our kernels are not as optimized as cuBLAS, so this advantage comes mainly from the increased arithmetic intensity and the overhead of splitting and merging the components of the complex elements. On the right, the gap becomes smaller because cuBLAS starts to catch up very well with performance, so the gap shrinks from 70% to 24%. So if we go for wider panels, yes, cuBLAS can take over our kernel, but the entire performance of the factorization will be actually worse, because this is a mixed precision factorization. So we are doing the panel in FP32, while the rank updates are in mixed FP32 and FP16. So we spend more time doing FP32 if we go for wider panels. So if you increase beyond 512, this is what we experience, the factorization will actually be slower than these two sizes. So these are results for mixed precision LU factorization, single complex. This is what we need for our solver. From bottom to top, this is a full double complex factorization, and this is a full single precision factorization, so you'd expect 2x speed up, that's normal. And in MAGMA, we have two modes of doing the factorization. So we can do the panel on the CPU or on the GPU. If you do on the GPU, you have the advantage for small sizes. And if you go for big matrices, there is an advantage for pushing the panel on the CPU. So all in all, you can get an asymptotic speed up of about 5.1x against a full double complex factorization. And these speed ups here, these are our performance upper bounds. We cannot get higher speed up than that for the entire solver. So this is the performance gain, and then the GMRes and the iterative refinement will actually consume some of this performance gain until we converge to the accuracy that we are looking for. So this is just an example to show how good the GMRes based iterative refinement is. This is a single complex matrix of size 20K by 20K. It has a two norm condition number of 10 to the 5, and converging to single precision would require 10 iterations of GMRes, but actually more than 100 iterations for classical iterative refinement in order to achieve a single precision accuracy. And there are many, many examples where we see that GMRes is usually superior to classical iterative refinement. Now, the final performance of the solver, this is a dual precision solver, so solving from solving for single complex accuracy using half complex precision. So on the left, this is a best case scenario. So this is a diagonally dominant matrix with a very, very small condition number, just to see what's the limit or what's the performance gain for our solve. So asymptotically, we can get up to 2.5x of performance speedup against solving in full single complex precision. If you try a harder matrix, so this is a matrix with clustered singular values, the two norm condition number is order 10 to the 4, so the asymptotic speedup drops from 2.5x to 2.2x because GMRes requires more iterations. So on the left, we converge in about 1 or 2 iterations, so things are good and there is no overhead in the iterative refinement, so we get all the performance gain from the factorization propagates to the entire solver. If we require more iterations for convergence, then you would expect less or smaller speedups. This is very preliminary results for double complex, so this is a triple precision solver. And again, this is a very nice matrix, very small condition number, just to see how far can we go with the performance. So asymptotically, it's 4.9x against solving in full double complex precision. And if you try a harder matrix, so this is a Hermitian matrix with mixed sign eigenvalues, so it cannot be solved with Cholesky, then the performance drops from 4.9 to 3.8, again because of the increased number of iterations in order to converge to double complex accuracy. Now I'll switch to very recent work that we are doing in Cholesky-based solvers. So we are using left-looking Cholesky factorization in order to use BLAS. This is for real arithmetic, so we are not yet done with the complex precision. So for real precision, we can just use BLAS. We don't need our kernels here. And this, we also do some pre-processing steps that can ensure Cholesky factorization to succeed, because the matrix can lose its positive definiteness when you convert to FP16. So there are kind of 3 steps. So we do 2-sided diagonal scaling, followed by a diagonal shift, followed by another scaling, in order to make better use of the dynamic range in half precision, and to ensure that the Cholesky factorization will succeed. So this is not a best case scenario. The best case scenario is around 4.7 faster than doing a full double precision solve. So, but this is a matrix with a relatively high condition number. So the infinity norm condition number is around 10 to the 9. And we can get up to 4.4 times performance speedup against a full double precision solve. Another slide that can be a little interesting. So from bottom to top, this is a full double precision solve, around 6 teraflops of performance on the V100. If you use the dual precision with classical iterative refinement, you get around 1.7, 1.8 speedup. And now if you use the FP16 with a 0 shift, so here the pre-processing is really crucial. If you use mixed precision FP16 with a 0 shift, then I think we need around 30 to 35 iterations in GMRes in order to converge, which consumes most of the performance gains that we had in the factorization. And this means that probably the low precision factors of A do not serve as a good preconditioner for A during GMRes. Now, when we shift, and C equal 10 here mean 10 times the machine epsilon in half precision. So when we do this perturbation on the diagonal of the matrix, we can actually get better speed up, because GMRes requires around 15 or 12 iterations in order to converge. So that shows that the iteration count is really crucial for convergence, because you are just consuming from the performance gains that we had in the factorization. So if you shift, you get 3.2x speed up. If you don't shift, you get 2.2 speed up. And this is just for the very, very large matrices. So this is my talk. So in general, thanks to some recent algorithms, FP16 is not only for machine learning. This is one case for linear algebra. I think the whole mini symposium is about that. It led to a new family of mixed precision solvers where we can achieve more than 4 times speed up of for very large matrices against double precision solve. And since NVIDIA is already here, please, if you can provide half complex kernels with interleave format, that would be great. And we're still having some missing steps to do. So we don't do matrix preprocessing for general matrices, and we didn't have yet the complex case for Hermitian positive definite, and we are yet to look into some more FP16 kernels. Thank you. That's it.